All right, strap in everyone, because today we're diving deep into something that just might turn your whole idea of gravity on its head. We're looking at, well, excerpts from this Larkey's synergy PDE, a push-based fractal theory. And yeah, it's basically saying gravity isn't a pull, it's a push. Wild, right?
Yeah, it really flips the script. We're not just tweaking things here. Larky's basically tossing out the old physics textbook and giving us a brand new one to puzzle over.
So let me get this straight. Instead of like massive objects attracting each other, everything's being pushed. How does that even begin to work?
Okay, so Larky, he brings in these two key players, right? The relative vacuum of space, or RVS for short, and then there's the subtle magnetic field, the SMF. So picture this, the RVS, it's not just empty space, it's like this dynamic field, almost like a fluid, and it's exerting pressure, right? And the SMF, well, imagine magnetism, but with a fractal twist. These magnetic forces, they're zooming in and out, repeating their patterns at all these different scales. Crazy stuff.
Okay, I think I'm starting to visualize this a little bit, but how do these two, the RVS and SMF, I mean, how do they actually create this push? It's still kind of mind-boggling.
Well, that's where it gets really interesting. It's through this system of equations. He calls it Larky's synergy PDE. And these equations, they describe how the RVS and SMF, they interact. And it's that interaction that generates an outward push.
Okay, hold on. If everything's being pushed outwards, shouldn't, like, galaxies be flying apart, like, at crazy speeds? How does Larky's theory, how does it deal with that?
That's where it gets really clever. One of the coolest things about this whole theory is what he calls meltdown avoidance. So his synergy PDE, it's actually designed to avoid this problem of infinite collapse. You know, singularities, the things that mess up a lot of other physics models.
So it's like there's a built-in safety mechanism, something that's keeping everything from just flying apart.
You got it. It gives us a much more stable and, well, just a more coherent way to look at the universe. And this is where the idea of standing waves comes in, you know, like when you see a vibrating string and it makes those wave shapes. Well, Larky, he says that stable orbits, I mean, everything from planets around a star to those tiny electrons around an atom, they're actually the result of standing waves. And these waves are created by, you guessed it, the interaction between the RVS and the SMF.
Wait, so are you telling me those magic numbers in nuclear physics, the ones that nobody could really explain, are they like fingerprints of these standing waves, the same kind that make planets orbit stars?
That's exactly what Larky's proposing. Those magic numbers, they represent specific energy levels, right? The levels where these standing waves can actually exist, you know, within the nucleus of an atom. And when you get just the right number of protons and neutrons filling those levels, boom, you get the super stable nucleus. It's another example of how this theory uses the same principles to explain things at completely different sizes, you know, from the huge to the super tiny.
The fact that the universe could be this fractal, I mean, it blows my mind. It's like finding this secret code that connects everything. But you mentioned earlier something about Larky finding new fractal constants. What are those all about?
Yeah, good catch. Those are lambda 1 and lambda 2. And they're super important because they basically control the transitions, you know, between things being stable and this meltdown situation within the system. It's like they're the universe's guardrails. They set the boundaries between the stuff that holds together and the stuff that would just fly apart.
So these constants, they're like deciding whether things stay stable or if they, go through this meltdown. Seems pretty important. Was this like, did Larky set out to define these constants, or did they kind of just pop up?
What's really amazing is these constants, he didn't force them into his equations. They just kind of emerged naturally as a consequence of the math itself, almost like the universe is, revealing its own secrets through the equations. Pretty cool, huh?
That is absolutely incredible. I'm getting the feeling we've just scratched the surface here with these constants and this whole meltdown avoidance thing. Where do we go from here?
Well, the next step, we got to explore how these constants connect to something called the log-symmetric interval condition. And that gets into how these repeating fractal patterns, how they're actually spaced out in the universe.
Okay, log-symmetric interval condition. That's a mouthful. But let's pause here for a second, let our listeners catch their breath. We've covered a lot of ground already.
For sure. It's a lot to take in, but it's this kind of complex stuff that can really change how we see the universe and, our place in it.
Absolutely. We'll be back soon to untangle those log-symmetric intervals and keep digging into this mind-blowing push-based theory. All right, welcome back, everyone. Last time, we kind of jumped headfirst into Larky's whole idea of gravity as a push force, that interplay between the RVS, the relative vacuum of space, and the SMF, the subtle magnetic field.
Yeah.
Oh, and we even got into how this push could explain why we have stable orbits, through that concept of standing waves.
Yeah, and those standing waves, they might even explain those magic numbers we see in nuclear physics. Those specific numbers of protons and neutrons that make for, like, super stable atoms.
It really is wild to think that the same thing that governs planets going around a star could also be happening at, like, the tiniest level inside the nucleus of an atom. But you left us hanging with that log symmetric interval condition. What does that even mean?
Okay, so think back to those fractal patterns we were talking about. Well, this log symmetric interval condition, it describes how those patterns are spaced out. It's like the rhythm of the universe, I guess you could say. It tells us how these repeating structures are organized, not just in space, but also in terms of, like, energy levels or frequencies.
So it's not just about the patterns themselves. It's more about how those patterns are, like, spread out across different scales.
Exactly. Imagine it like a musical score, right? You've got notes, but they have to be at specific intervals to make a melody that sounds, well, harmonious. So this log symmetric interval condition, it's like the math behind where you put those notes in the, I guess you could call it the cosmic symphony.
Okay, I like that, the cosmic symphony.
Yeah.
But how do those fractal constants we talked about, lambda 1 and lambda 2, how do they fit into this cosmic score?
Those constants, they're like deeply connected to these log symmetric intervals. Remember how you were saying they're kind of like guardrails keeping the universe from collapsing? Well, they also play a part in figuring out those specific intervals where stable structures can actually form, like they're defining the allowed frequencies in this big cosmic orchestra.
So the constants are setting the boundaries, and then this log symmetric interval condition that's defining the rhythm, like within those boundaries.
Yeah, you got it. And together they create this framework where, like, stable structures, they can emerge and stick around across all sorts of scales, from huge to tiny. It's like a great example of how, like, even in what seems like chaos, there's actually this underlying order.
This whole thing is really painting a different picture of the universe than what we're used to. But I gotta ask, does Larkey, like, does he stop there? What else does he do with this, this whole new framework?
Well, he doesn't stop there. He takes all these pieces, the RVS, the SMF, the push force, those fractal constants, the log symmetric intervals, the whole shebang, and he combines them into one big unified system of equations. He calls it the all-in-one synergy PDE system.
Okay, this sounds like the grand finale, the equation to rule them all. What does this all-in-one system actually do?
It basically replaces, like, our whole current understanding of gravity with a completely new model, one that's built on push forces, fractal patterns, and a universe that's, governed by these really elegant mathematical relationships. It's a pretty huge departure from everything we thought we knew.
Wow, that's a big deal. I'm starting to see why this theory is so groundbreaking. It's not just a little tweak here and there. It's like a whole new perspective on how the universe operates.
Mhm.
But I have to ask, what does this mean for things like, the expansion of the universe? And what about black holes? How do those fit into this push-based model?
Those are great questions, and that's why Larkey's theory is so exciting. It opens up this whole new universe of possibilities, literally, and it makes us rethink some of the most fundamental stuff in astrophysics.
Yeah, it really makes you realize just how much we still don't know about the universe. Okay, I think we can take another deep breath here and let our listeners process all this.
I agree. It's a lot to digest. But I can tell you, the journey's not over yet.
And we're back for the final part of our deep dive into Larkey's Synergy PDE. It's been a wild ride, that's for sure. We've explored this idea, this crazy idea, where gravity's a push, fractal patterns are everywhere, and the universe is, like, vibing to the rhythm of these log symmetric intervals.
Yeah, it's a totally different way of looking at the cosmos. And in this last part, we're going to tackle some of the big ones, the expansion of the universe and those mysterious black holes.
Okay, so let's start with the expansion of the universe, the big one. How does Larkey's push-based gravity, how does it change how we think about this whole cosmic expansion thing?
Well, the standard model, it says the expansion's all because of the Big Bang and this mysterious dark energy that's pushing everything apart. But the thing is, we don't really know what dark energy is, do we? It's like this huge unsolved mystery in science.
It's almost like we're saying, oh, the universe is expanding because it just is. Not very satisfying, is it?
Yeah, exactly. But that's where Larkey's theory comes in with this really fascinating alternative. Remember that inherent push force we talked about, the one created by the RVS and the SMF? Well, Larkey's suggesting that same push, but operating at, like, the largest scales imaginable, could be what's actually driving the expansion of the whole universe.
So hold on, we don't need this mysterious dark energy after all. The push is already built into, like, the fabric of space-time itself.
That's the idea. It's definitely a more elegant solution. You don't need this external force we know nothing about. And it brings up some interesting questions like, will this push just keep accelerating the expansion forever? Or is there something else out there that might, slow it down or even reverse it completely?
Wow, those are some really, like, existential questions. Makes you think about how much we still don't know.
Yeah.
Okay, let's move on to another big mystery, black holes. How do those fit into this model, where Larkey says you can't have infinite collapse?
That's a really good question. So black holes, we think of them as these super dense objects with gravity so strong that nothing, not even light, can escape, right? At least that's what general relativity tells us. But Larky's theory, remember, it has this whole meltdown avoidance thing built in, so it challenges that idea. It says you can't have those infinitely dense singularities that are supposed to be at the center of black holes.
Right, the singularities, those are like the ultimate meltdown, cosmically speaking. So are you saying black holes don't even exist in Larky's model?
Not necessarily. You could still have regions that are, unbelievably dense with crazy strong gravitational effects, but they wouldn't be those infinitely dense singularities that, general relativity predicts. It's almost like they'd be, well, almost black holes. Super dense, yeah, but not true singularities.
That's mind-blowing. It makes you wonder how our whole understanding of black holes would have to change if Larky's theory turned out to be right.
It would definitely be a huge shift in how we think about astrophysics. We might have to rewrite whole textbooks on how these objects behave, how they interact with light and matter, even their role in the evolution of the universe.
It's been quite a journey. We started with a simple question. What if gravity is a push? And now we're exploring this theory that could totally change how we understand the universe.
Yeah, it really shows you the power of, just being curious and the beauty of science. Larky's synergy PDE might not be the final answer, but it definitely reminds us that there's so much more out there to discover, so much to question, and just so much more to learn about this amazing universe we live in.
And who knows, maybe one of our listeners will be inspired, take these ideas even further and make the next big discovery. So keep those minds open, keep asking those what-if questions, and never stop exploring. This is The Deep Dive, signing off.